Hello, I am Kwang Kim, and I will be presenting hammer filter, robust protection, and low hardware overhead method for RowHammer. This is the outline of my talk. First, I will start by introducing some background on RowHammer. I'm going to explain what RowHammer is. Repeatedly access to a DRAM row, which is called aggressor row, causes bit flip in nearby rows. The row which occurs bit flip is called victim rows. This phenomenon is commonly referred as RowHammer. I will explain why RowHammer is crucial to solve. First, RowHammer can be used to make malicious application, so it incurs security problem. There is an example that gains kernel privileges on x86-64 Linux. It destroys DRAM data in modern computer systems. Secondly, as DRAM process technology scales down, RowHammer is getting worse. The RowHammer threshold, which means how many times the row should be accessed to incur RowHammer, gets low. It makes multiple aggressor rows can be used to attack, so attack patterns are getting complicated. Also, new attack patterns have been being introduced like double-sided attack, half-double attack. So, RowHammer problem becomes more difficult to be handled. I will explain various attack patterns more on next slide. There are several RowHammer attack scenarios. Double-sided attack accesses both sides of a victim row like a figure, so it makes the victim row between two aggressor rows more vulnerable to RowHammer attacks. The other example is that complicated RowHammer attack can be made using multiple aggressor rows. Now, I will introduce existing solutions for RowHammer. There are two types of hardware-based protection methods for RowHammer: probabilistic methods and counter-based methods. Probabilistic methods perform additional refreshes with a certain probability to solve RowHammer. They can be implemented with simple hardware circuit, but they have low protection performance. On the other hand, by keeping track of every aggressor rows using counters, counter-based methods handle RowHammer. They can guarantee protection but still suffer from considerate area overhead or extreme additional refreshes which are related with performance overhead or even both. There are several previous probabilistic methods for RowHammer attacks: para, analog, and prohit. This graph is the result evaluated with the aforementioned attack pattern. X-axis is the number of aggressor rows, and y-axis is RowHammer reduction ratio. As described in the graph, most of models cannot prevent well for all ranges of the number of aggressor rows. There are also several previous counter-based schemes. Twice and graphene cause significant hardware overhead to operate them compared to our proposed scheme. And the CBT not only requires a large hardware overhead but also carries out considerable additional refreshes to prevent RowHammer attacks. I'm going to explain our motivation and goal. Prior hardware-based methods have limitations. They cannot prevent complex RowHammer attack or require tremendous area overhead or cause many additional refreshes. In other words, they cause performance overhead. Therefore, our goal is suggesting a novel solution that provides protection against RowHammer even in the complicated attack patterns. Also, it should operate with low area overhead and low number of additional refreshes. Based on the aforementioned motivation, we design hammer filter. First, I will introduce key idea and overview of hammer filter. Based on the fact that each row has different degree of threat to cause RowHammer, hammer filter tracks the degree of threat of each row with modified counting blue filter and performs additional refreshes them with a different probability according to the level. Next, I will give you a brief overview of hammer filter. Hammer filter decides the degree of threat based on access frequency, and access frequency is tracked with basic operations of counting blue filter, insert, and count. We introduce a new operation to counting balloon filter, half delete, to reduce the level of threat of refreshed rows because refreshed rows have no risk of incurring RowHammer for a while. So we can reduce unnecessary additional refreshes. I will explain why half delete. This figure is an example of delete operation which subtracts each value in the hashed positions by count value. If delete green row from the count table, it subtracts each value by 3 because count value of green row is 3. After delete operation, it impacts on other accessed rows count value. Count value of red row decreases 4 to 3 and count value of blue row decreases 1 to 0. It is referred to hash-induced collision and it has negative effect on additional refresh probability. On the other hand, half delete operation subtracts each value in the hashed positions by 1/2 of the count value. In the figure example, because the count value of green 1 is 3, half delete subtracts each value with 1. After half delete operation, there is no impact on other rows' count value. Therefore, it avoids a hash-induced collision in this case. I'm going to explain HAMMERFILTER implementation. HAMMERFILTER is totally implemented with hardware in the memory controller. Counter table stores access frequency of each rows. In HAMMERFILTER, counter table has 3,961 entries, and each entry consists of 3 bits. Hash unit hashes the given element to k bits, then each bit is assigned to counter table's indices and added. Insert logic updates aggressor row candidates with a certain probability to the counter table. Delete logic reduces aggressor row candidates value in the counter table when additional refresh is done. Count logic provides the extent of danger of accessed rows to the refresh logic. I'm going to explain HAMMERFILTER's operation. By using insert operation, HAMMERFILTER inserts an accessed row to the counter table with a fixed probability pi 0.005. Simultaneously, count logic sends count value to the refresh logic for every access. Refresh logic sends additional refresh commands to the between rows with the probability according to a specific equation below. When additional refreshes are performed, delete logic performs half delete. Next, I will explain the details of our experimental methodology. We use DRAM Scene 2 integrated with Gen 5 as the DRAM simulator for performance evaluation. We set RowHammer threshold as 4K, which is smaller value than the recently reported value, considering that RowHammer will worsen in the future. For workload, we use 19 benchmarks from Spec CPU 2006 for benign applications, and 5 patterns are created based on the previously described attacks for malicious applications. I will move on to our evaluation results. This is the result of RowHammer reduction ratio in malicious applications. X-axis is the number of aggressor rows, and Y-axis is RowHammer reduction ratio. The results in the figure are average number obtained from 5 patterns. The figure shows that previous probabilistic methods cannot prevent RowHammer from malicious attacks. On the other hand, HAMMERFILTER achieves superior results. This slide describes analysis of additional refreshes in benign application. X-axis presents benign applications, Y-axis is relative number of additional refreshes. HAMMERFILTER performs a small number of additional refreshes, 1.5% of basic refreshes on average, which has little effect on system performance. We analyze area overhead of HAMMERFILTER compared to counter-based methods. X-axis is each RowHammer protection method, and Y-axis presents area cost. As described in the figure, HAMMERFILTER requires smaller storage. Is 40.6 times better than twice and 2.3 times better than graphene. Let me conclude my presentation. HAMMERFILTER is a novel method to mitigate RowHammer. It provides robust protection for RowHammer attacks, has negligible performance overhead, and operates with less area cost compared to previous counter-based method. Thank you for listening.